Today we are going to start the second chapter, Numbers and Sequences. The topic is Euclid's division lemma. Let a and b, a greater than b, be any two positive integers. Then there exist unique integers q and r such that a is equal to bq plus r. Let us try to understand this with a simple example. This is a division sum. We are dividing 13 by 3. 13 is called the dividend, 3 is called the divisor. So let's do the division. 3 4s are 12, 13 minus 12 is 1. So this I'm going to write it in this form of a is equal to bq plus r. A is the dividend, 13 is equal to b. B is the divisor. Always remember, we are dividing this a by b. It's called the divisor. So a is equal to bq, that is the quotient, plus r. Okay, the remainder. So I can easily, you can see 13 is equal to 3 into 4 plus 1, where 3 is the divisor b, q is the quotient 4, and r is the remainder 1. So any two numbers, okay. So the lemma says that any two numbers a and b, where a should be always greater than b, that you should be careful. Any two positive integers, then it can be written in this form a is equal to bq plus r. That is what the lemma states. It will be very clear when we do sums. Here another important thing to remember, when remainder is 0, we can say that a is divisible by b, or we can even say b divides a. Okay. Let's go to the first sum. Find all positive integers when divided by 3 leaves remainder 2. So here they have given us the divisor. It is divided by 3. So b is equal to 3. Remainder r also they have given 2. They are asking us to find all positive integers which are divided by 3. What it means? We have to find all the values of a. Okay? Because a only is divided by 3. Okay, so let's write down the lemma here. A is equal to bq plus r. So a is equal to 3. B is given 3q plus 2. Remainder is also given. So here we are going to put different values of q, that is positive integers for q, and find the corresponding values of a. Let q be 0. You get value of a as 2. Q be 1. A is equal to 5. Q is equal to 2, A is equal to 8, Q is 3, A is equal to 11, dot, dot, dot. Okay. So, the positive integers which are 2, 5, 8, 11, dot, 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 which when divided by 3 will give us a remainder of 2. A man has 532 flower pots. He wants to arrange them in rows such that each row contains 21 flower pots. Find the number of completed rows and how many flower pots are left over. So here it's a simple division sum. Okay, here a, the dividend is 532, and we are going to divide it by 21. That is the divisor, that is b. Now let us substitute this in the lemma, Euclid's lemma. Write down the general form. Now a is equal to 532 is equal to b 21 into, now we need q and r. You have to do the division for it. You will get the value of q and r. Write it down. So this is the lemma. So on this we can say that the number of completed rows is 25 and the remainder, the leftover flower pots, is 7 pots. Question 3. Prove that the product of two consecutive positive integers is divisible by 2. Okay. Let two consecutive positive integers be n. So if the first integer is n, the next integer will be n plus 1. Your teacher may have taken the first integer as n minus 1 and the second integer as n. That is also correct. I have taken it as n and n plus 1. Okay. So we have to do the product of two consecutive positive integers. So let us multiply them. You get n square plus n. Okay. Now we have to prove that it is divisible by 2. Okay. So the positive integers divisible by 2 is of the form 2q or 2q plus 1. This is the general form for the integer. So let n be 2q. First case, let us put n is equal to 2q. Substitute here in this product. Okay. Open the brackets, you get 4q square plus 2q. Take out 2q common, you get 2q plus 1 within the bracket. So here you can write it as 2m, where m is equal to q into 2q plus 1. So here you can see that the factor, one of the factors is m. So that means this is divisible. One of the factor is 2. Therefore, it means that this is divisible by 2. So n square plus n is divisible by 2. The second case, we are going to take n as 2q plus 1. So let us substitute here. So here it is, open the bracket. This is a perfect square. So 4q square plus 4q plus 1 plus 2q plus 1. So this becomes 4q square plus 6q plus 2. Take out 2 common. So you get this. So write down this is equal to 2m, where m is equal to this expression. So again, 2 is a factor here. Hence, n square plus n is divisible by 2. Question 4. When the positive integers a, b, c are divided by 13, the respective remainders are 9, 7, 10. Show that a plus b plus c is divisible by 13. So these are the positive integers. When divided by 13, leaves remainder 9, 7 and 10. So let's write down the first lemma. A is equal to, it's divided by 13. So 13q plus the remainder is n. A is equal to 13q plus n. B is equal to, again, divided by 13, 13, q quotient we do not know, leave it as it is, plus the remainder is 7. C is equal to 13q plus 10. Okay, you have written it down. Now add the LHS because that's what we want here. So you have to add the RHS also. So 13q plus 13q plus 13q is 39q. 9 plus 7 plus 10 is 26. Take out 13 common, you get 3q plus 2. So 13m, where m is equal to 3q plus 2. So here you can see that a plus b plus c is divisible by 13. Question 5. Prove that the square of any integer leaves the remainder either 0 or 1 when divided by 4. Let x be the integer, its square is x square. So now there are two cases where x can be an even integer. So the general formula is x is equal to 2m, x square is equal to 4m square. Write it in the form of lemma, x square is equal to 4m square plus 0. Okay, this you can write. So this means that x square is divisible by 4 and it leaves a remainder 0. Okay, second case is when x is odd. So this is the general formula, x is equal to 2m plus 1. So x square is equal to 2m plus 1 whole square. Square it. So here take the first two terms, take out 4m common, m plus 1 you get plus 1. So write down this as 4q plus 1, where q is equal to m into m plus 1. So here you can see that x square is divided by 4 and it leaves a remainder 1. So here we have come to the end of sum 5. The rest of the sums of the same exercise 2.1 I have put in a separate video. You can go through that also.